All right, ladies and gentlemen, so welcome to this particular class where we continue preparing you guys for your exams, for tests, for quizzes, and any other sort of assessments. Now, before we even begin, I'll just love to remind you people there's a quote that this lecturer, Mr. D. Temple, that he always includes in his notes to say hard work always beats talent, which means even though you have the talent, if you're not putting in enough work, that talent cannot develop to bear any sort of fruit. So I would love also to connect that to a quote that says top students are mostly not always the smartest, but people who understand concepts better. And that is exactly what we do here as Discrete Learning Institute. Our goal is to try and simplify difficult concepts for students to understand in our pre-med courses. You can talk about biology, you can talk about chemistry, physics, but also mathematics and many other courses. So we simplify the concepts so that we make them as simple as possible for the students to assimilate. So welcome again. Let's continue together and don't forget to register with us using the details that are provided in the description. Thank you very much. Enjoy the lesson. So let's solve these questions that are about thermal energy, but also heat. And question one is saying, or question one, part one is reading, an ice cube of mass 50 grams is placed in a room at 20 degrees Celsius. If the heat of fusion of ice is 334 joules per gram, how much heat, how much heat energy is required to completely melt the ice cube? If the heat of fusion of ice is 334 joules per gram, how much heat, how much heat energy is required to completely melt the ice cube? Okay, so the basic concept behind this question is that when you are melting heat or when you are melting any other substance, that substance is supposed to absorb heat. So it absorbs heat at a constant temperature, which means without it changing its temperature. To change its phase from one phase of matter to another, of which in this particular case we are describing from a solid to a liquid, or from ice itself to liquid water. So that heat that is absorbed by the ice, the Q, that is absorbed depends on the mass of the ice that you've been given, but also the latent heat of fusion. The latent heat of fusion. Now, in this particular question, they're asking us, see how much heat energy is required to completely melt the ice cube, which means we're trying to calculate the heat, which is the Q here, that is being absorbed, and you said it depends on the mass of the ice that you've been given, but also the heat of fusion of ice. So now that I've already jotted down the formula here, we're just going to note down what we've been given in this particular question. So the mass, they've given us to say the ice has a mass of 50 grams, but they've also given us the heat of fusion of ice to say the latent heat of fusion is equal to 334 joules per gram, like this. This is what we've been given. So what do? We just have to plug in these values into our formula. So I'm going to say my heat of fusion, Q, will be equal to mass, which is 50 grams, multiplied by the latent heat of fusion, which is 334, like that. So my Q will be equal to, let me just punch this in. This is giving me 16,700 joules. 16,700 joules of energy, which means the amount of thermal energy which is required or which needs to be absorbed to melt 50 grams of ice at a constant room temperature of 20 degrees Celsius is 16,700 joules, and that is that on part one. Part two is saying if all this heat is supplied in 2 minutes, what is the rate of heat transfer in watts? If all this heat is supplied in minutes, what is the rate of heat transfer in in watts. Okay, so in this particular case, they want us to calculate the rate of heat transfer. When you just hear the word rate, that means we are talking about the amount of time that is taking, or that it's taking for a specific action to take place. So here, or in general, the rate of heat transfer is just the amount of heat that is transferred per unit time, of which it's more like we are just describing power. So what are we going to say? We're going to say the power here, which is the rate at which the heat is being supplied, will be equal to the heat itself divided by time, where this is power, this is the heat energy itself, where T is time, like that. So the heat energy we've already calculated in part one to say it's 16,700. 16,700 joules, like that. Then time, they've given us to say this is being supplied in what? In 2 minutes. Which if I multiply this by 60, I'm going to get 120 seconds, like that. So that means here we're even done with this particular question, because the only thing that remains is now plugging into the equation what we already have. So this will be 16,700 divided by 120, like that. So 1670 divided by 12, this is going to give us the power at which heat is being supplied to be equal to 139.17. 139.17 watts. Can put the whole word watts, or if you want, you can just put capital W. They'll understand to say it watts. So that is basically it, ladies and gentlemen, about this question. We've calculated the amount of heat that is required to melt the ice cube, which we've just said it depends on the mass and the latent heat of fusion of ice. Then we've also calculated the rate. The rate of heat transfer, which that basically means the power. It's the time that it's taking for a particular action to take place, of which in this particular case, it's the heat being transferred. So we'll just say our total heat that is being supplied divided by the total time that it's taken, and we're getting an answer which is equal to 139.17 watts. As simple as that. And we are done with this particular question. Let's move on to the next one. Question 2 reads, a metal rod 1 meter long and of cross-sectional area 1 cubic centimeters is heated one end to 100 degrees Celsius, while the other end is kept at 20 degrees Celsius. The thermal conductivity of the metal is 20 watts per meter degree Celsius. Part A, how much heat flows through the rod per second? How much heat flows through the rod per second? And part B, if the temperature at the midpoint of the rod is 60 degrees Celsius, what is the temperature, or what is the temperature gradient at that particular point? What is the temperature gradient at that particular point? So let's start with our part A. And if we look at this question in general, we are talking about heat conduction in a metal rod. So the way heat flows, we know to say heat is always flowing from a hotter environment or a hotter system to a system that has a lower temperature. It is always moving along the concentration gradient, or can I, since it's heat here, can we still say concentration? I don't know, but it's from the higher temperature to a lower temperature, like that. And as heat is flowing, the rate at which heat is flowing depends on several factors. It depends on the thermal conductivity, which we've been already given in this particular question. It depends on the cross-sectional area, which we've already been given in this particular question. It also depends on the temperature difference. The temperature difference, which means uh, the difference between the two ends, the environment where heat is flowing from, and the environment where heat is flowing to. but it also depends on the length of that particular material. And since in this particular case, we're talking about a metal rod, they've already given us the length of this metal rod to say it's 1 meter long. So to come up, or the principle that we are using to combine all these equations into one relationship, what do? We follow what we call the Fourier's law. We use the principle that we call Fourier's law. And what does it give us? Remember, we're talking about rate of heat conductivity. We're talking about heat conduction. They've asked us about the rate of heat flow, like that. So in question one, we're from calculating rate of heat flow. We said it's represented as Q over T, which is the power, generally the power. And this is equal to what according to Fourier's law? Say rate of heat flow is equal to K multiplied by A multiplied by delta T divided by L, where K here is the thermal conductivity, which we've been given in the question. Then we have this guy that is here, which can also be represented as capital H, which is representing heat flow per second. We have cross-sectional area. We have the temperature difference here, which means the final temperature minus the initial temperature. Then we have length of the rod here, which means the rate will be directly proportional to the thermal conductivity, cross-sectional area, but also temperature difference. But it will be inversely proportional to the length of the rod, like that. So this is the principle that we're going to apply. Now, how we're going to solve this question is we'll get what we've been given first and make sure we have them in our SI units. For example, we've been given 1 cubic centimeter. We want to make sure that we have our 1 cubic centimeter in its SI unit form, of which 1 cubic centimeter. So for example, cross-sectional area is 1 cubic centimeter, which is just basically equal to 1 times 10 to the power minus 4 cubic meters, like that. Okay, then there's the temperature difference. They've told us to say uh, it's heated at one end to 100 degrees Celsius, while the other end is kept at 20 degrees Celsius, which means the temperature difference will be 100 minus 20, which is going to give us 80 degrees Celsius, like that. What else? They've already given us the length to say it's 1 meter. What else do we have? We have the K, which they've already given us in this particular equation. And what else have we been given? I think that is all. I think that is all. So we'll get what we have and plug it into the Fourier's equation. So I'm going to say for my part A, H, which is also the rate of heat flow, will be equal to K, which is 200 multiplied by cross-sectional area, which is 1 times 10 to the power minus 4, multiplied by temperature difference, which is 80, everything divided by the length, which is 1 meter. That means our rate, okay, our Q over T here will be equal to, just plug this in directly, 200 multiplied by 1 exponential minus 4 multiplied by 80 divided by 1. Okay, so this is giving me 1.6 joules per second. 1.6 joules per second, which is the same as 1.6 watts. So it's the same as we're talking about the power, the rate of heat transfer. So joules per second is the same as watts, just like that. Okay, then this is part A. Let's now move on to part B. And in part B, they're asking us to uh, calculate the temperature gradient. If the temperature at the midpoint of the rod is 60 degrees Celsius, what is the temperature gradient at that point? What is the temperature gradient at that particular point? The concept of temperature gradient just tells us how rapidly temperature changes with distance along this rod that we've been given here. And in order for us to calculate the temperature difference, we're going to say or rather temperature gradient, not temperature difference, temperature gradient. We'll say this is equal to the change in temperature, the total change in temperature divided by what? Divided by the length. The length of which in this particular case, it's the length of the rod, or the total length of the rod. So this is going to be equal to what? Remember, initially we said the temperature at one end is 100 degrees Celsius minus the temperature at the other end, which is 20 degrees Celsius, divided by the total length of the rod, which is 1 meter. This is going to give us what? This is in meters, this is in degrees Celsius. This is going to give us 80 degrees Celsius divided by 1 meter, which means the temperature gradient is equal to what? The temperature gradient is equal to 80 degrees Celsius per meter. This is the temperature gradient in this particular case. Or alternatively, since they've told us to say the temperature difference at the midpoint of the rod is 60 degrees, what are we supposed to do? We're now supposed to reduce the length that we're using here, which means we're changing the values. Let me use a blue pen. We're changing the values. If I say change in temperature divided by total length, I'm going to say the temperature change here is from 100 to the midpoint, and the midpoint is at 60 degrees Celsius. So I'll say 100 minus 60, and this is in degrees Celsius, like that, divided by the length. The 60 degrees Celsius is at the midpoint of the rod, and at the midpoint of the rod, if the total length of the rod is 1 meter, at the midpoint of the rod we're going to have 0.5 meters, so which means the length that I'm plugging into this equation is 0.5 meters, like that. And this is going to give me how much? This is going to give me 40 at the top. So give me 40 degrees Celsius divided by 0.5 meters, which is still going to give me 80 degrees Celsius per meter. So that is that, ladies and gentlemen, when it comes to calculating heat flow through the rod, but also the temperature gradient. So one thing you're supposed to remember is that temperature gradient is just representing the rate of change of temperature with respect to distance along this particular road that we've been given here. Very important. So it basically, can I say it is describing how fast the temperature drops as you are moving from the hot end to the cold end. And the formula is the change in temperature, which is the temperature difference between the two ends, divided by the total length that you are dealing with. That is that on this one. Let's move on to the next question.